Hello everyone, July the 6th. Alright, today is the day. We got an easy problem, so we have to at least do one of these, okay? Definitely do this one first, because kth ancestor of a tree node, that is required. I want to use this algorithm to solve this problem, so we need to do this one first. We'll do this one. I mean, it's a hard problem, so it's good. And we have algorithm laying around, so we'll do this. Actually, this I can actually add. This is a good interview question, right? It's a good interview question because it is a tough question if you have a list of queries and you don't know what the queries are. That is hard, right? You don't know what these are. They come by one. That's a hard question. However, if you know them already, if you know this whole thing already, then it is not hard because you can prepare, right? You can prepare the ancestor list, so it's not going to be a difficult question. So this I think I can use in the future for if I need to give interview questions. All right, let's do this. Water bottle.
Oh.
There are num bottles, water bottles, that are initially full of water. You can exchange empty water bottles from the market with one full water bottle. The operation of drinking a full water bottle turns it into an empty bottle. Given the two integers, number of bottles and number of exchanges, return the maximum number of water bottles you can drink. So we have 9 bottles, 3 empty to get 1. So we do 3. Wait, hold a second. The operation of drinking a full water bottle turns it into an empty bottle. So we go 3 replace 1, 3 replace 1, 3. So we can have 3 bottles, and they become empty. They can exchange for another one. So we got this. So in total, you have 9 plus 1 plus 3, 13. Okay, so what we can do is just divide, right? 15 divided by 4 is 3 mod 3. So you add that to become 6. So 6 divided by 4 is 1. You mod 2, so that would be 3. And that's it, we have 3 and left. Yeah. So we'll do this. Maybe there is a math solution. It's possible. Num bottles. Okay. Num bottles. And then we'll do next num bottle. So current. Also num bottles. While current is larger or equal to num exchange. Int no, it doesn't have. So empty, not empty, it's a full. So it's num bottles, not current. And then current rest plus equal to full, right? So I can just do num exchange and current equal to I need to use it again. So full right? And then current shall equal to current minus full, not current minus full, current mod num exchange plus full. Because when I go become those full, I can drink them, right? I can drink them to become empty. So they are wait, hold a second. We'll exchange, right? Every 3 we can exchange 1, 3 exchange 1. Oh, I turn the original into these with some left. So some left plus this full, right? These are newly created. So I add to the result, and then we reset the current, and then we try this again, and at the end we'll return res. Do. 100 bottles, let's say with 3. 3 bottles with 100. $100 a bottle is 3 bottles is 100. Yep. $15.18. Nothing more to say about this one. Optimize simulation. Yeah, I think that's about the same. Okay, now let's do this. Kth ancestor of a tree node. A tree with n nodes, Parent I is the parent of ith node. The root of the tree is node 0. Find the kth ancestor of a given node. The kth ancestor of a node is a kth node. Implement this class such that this initializes the object with the number of nodes. Return the kth ancestor node. Alright, so what we're gonna do is we need to traverse this. How do I traverse this? Yeah, I go from 0. I need to know what is its child. So I produce a tree here. because this gives you a parent. So you need a DFS, but DFS I need a parent. I need to go to my children. I don't know who my children is. You're telling me I need to convert this into, oh my god. Oh my god. Okay, so we're gonna go through this. So 0 go to 1, so I go 0, I plus 1. Okay. Yeah, it's fine. It's fine. That is fine because I believe this is necessary. So we need some Python here. 1483. Wow, interesting. Okay. Alright, let's do this. So what we need to do is a graph. For node v parent and enumerate parent. So graph parent dot append v, right? So that's where I get a graph out, and then I need to create a function that's called def build ancestors. Build an ancestor matrix such that ancestor v j is the j2 to the jth ancestor of node v. Doesn't that require a so I need to do here. So first of all, this has to be a self, right? So this has to be self, and self.ancestor equal to a default dict of a default dict. Now a default dict of a list of size max depth integer log 2n. Okay, so this one I need node parent and doesn't return anything. Alright, so we hit node and parent. It says self.ancestor node 0 equal to parent. Alright, we set that, and then we can set going all the way to its depth. I'm gonna go all the way to the top. I think that's fine. Maybe I should put a depth in it as well. Yeah, I think I should put it. Let's do a depth. Because there's n nodes, right? Yeah, n nodes, each one has a depth. Okay. This is the ancestor. And then depth, I probably need to also pass depth. Okay, so if that's a depth, then we can say j equal to 1 while 1 left shift j, right, is smaller or equal to depth then self.ancestor node j shall equal to self.ancestor something, which is self.ancestor node 0 j minus 1. Right, I want to find my 2 to the j's node. I look at should be 0. I look at the j minus 1, right? I want to from current find the j's node, 2 to the j's node. So I go halfway through, and then from there I look for its j minus 1, right? So when I start, the depth will be 1, or when I start, the depth is 0. So in this case, this will be 0, 1, right? So it's 1, 2, 3, so it should be 1. Yeah, so when we start, the depth is 1. Okay, the depth is 1. Okay, so we do that. Once we're done, we'll say self.build ancestor. We'll just say for child in self.graph node. So we need child. Enjoy. Node depth plus 1, right? Whatever depth it is, for depth plus 1. So this is the build ancestor. Okay, which means at this point we need to say self dot build ancestor, node is 0, parent, actually going to -1 because 0's parent is not, 0 doesn't have a parent. 0's parent is -1. Depth is 1. 0's depth is 1. Or 0 depth is 0. Good question. I think your depth, let's say if it's 0, no, it's depth 1, 2, 3, and this is depth 3, which means its depth is 0, 1, 2, 3. So I think it should be depth 0, right? It should be depth 0. Okay, so we build this ancestor. So now we build it. So now I have a node and I have a k, right? Kth ancestor. So we need to break k down into can we go from left to right? Yeah, we can right shift, but right shift doesn't really turn into a binary number. And can we just go from right to left? That's 0. And then we do from this, we'll do 2 times. Yeah, I think that should be fine, right? I can say while k if k and 1 is not equal to 0, and then we know we need to go yeah, that's not right. Again, we use the example of 7th, right? Somebody's 7th ancestor. So we start from someone, say, okay, then go to its 2nd. Hold on, I'm a little bit confused. Right, say we have a 7th ancestor is 1, 1, 1. So some node will go to its, this is 0, 1, 2. So go to the zeros. So go here, and from the zeros, next we need to go to its 1. Right, next we'll go to its 2. Really? Yeah, it's fourth ancestor. Yeah, so we also need I equal to, let's call j equal to 0, right? P equal to, I don't know P equal to what. So P shall equal to node. Huh. I try to do node. So P shall equal to self.ancestor P to the J. Right? K left shift equal 1, J plus equal 1. So every time we do, if it's a 1, I will get that many from the current position, and then we reset it. And at the end, we shall return P. Because at the end, yeah, so, okay. Default, this shall be a dict of integer and list. Oh, I did a list. Integer. Let's see if this one works. Huh. Something is not right. Yeah, we did not increment this. Sorry, feature plus equal 1. Interesting. Thanks. So we go to the children, alright? But the children shouldn't have any nodes, so we should end there. That's good, right? You have a node parent, we have node parent, depth is 0. So 0, 0 is minus 1. Depth is 0. And this which is 2 to the power. So we don't do this. So now we got a 1 and 2. Right? So now we go 1. 1 is parent is 0. Depth plus equal 1. Yes. So node is 1. 0 equal to 0. Depth is 1. Still not go. So we go 3, 4. So now at 3. Alright, I don't understand. Let's see, we can. Let's see if we have issue here. Oh, it probably won't give me any print. Shoot. Huh. Let's take a look at I'll just make sure if the graph is right. Oh no, this one's also. Oh, I think I know. It's not left shift. It's the right shift. Right? Yeah, it's the right shift. There we go. Yeah, it's a right shift. But I did forget about this. J into plus U1. Try it. Yeah, it should be ceiling. Yeah. Use binary lifting to create an ancestor matrix. Break K into its binary representation. Then we can use ancestor matrix to jump through each power, right? We can jump through the ancestor using 2 to the jth, using power of 2. Whew. Ceiling is not right. Really? A maximum depth. One, two, three, 4, 5, 6, 7, right? So the depth is 3, and the answer is 7. So whatever. So you're saying is int this plus 1. That's what you're saying. Int this plus 1. Because 7, we get answer is 2 point something. So int plus 1. Int this plus 1. Okay, int this plus 1. Yeah, this is very important. Yeah, this must be precise. The upper bound, right? The upper bound of depth must be precise. All right, we'll try it again. There you go. Okay. Yeah. Binary lifting. Pretty straightforward. We'll use a depth to do it. Yeah, we use a depth to do it. So we're gonna copy this one here. Yeah, binary lifting. Yep, +1. See that? So they use this to do so I guess it can make it simpler, right? I think it can make it simpler. You don't have to build a graph, right? Basically, that's what it is. You don't have to build a graph. You get a pre. You're gonna jump the current. Yeah, you know what? This is not that bad. I just do this, and then we do the build ancestors. Okay, so this is good. This is good. With this as our building block, we will use this to build this thing. Right? We'll use this to build. So basically, it's the same. We have edges. All the difference is we need to handle the weights, but it's okay. It's also a BFS, as a DFS, right? As we do DFS, we just use a counter, and we'll build this as well. Yeah. Okay. So I leave this, but I'm gonna implement this tomorrow. Okay, that'll be it. I'll see you guys tomorrow.